it's my honor to introduce the first speaker, my friend and colleague, Alberto Belloni. Alberto has this wonderful Italian accent, and he's always smiling. And much of that is because he's from Milan. And he hung out with Lake Como and places like that. So he's from this wonderful area. And he was an undergraduate at the University of Pisa and Scuola Normale, which is very prestigious in Italy. And then went to MIT for graduate school in 2002. He graduated 5 years later. He worked on the CDF experiment at Fermilab, which was a proton-antiproton collider. And he did some of the first measurements of B sub S mixing at the collider. And this turned out to be one of the most important things CDF did in its last 10 years. He then did a postdoc at Harvard, where he worked for Melissa Franklin and worked on the Atlas detector. He got his foot in the CERN door and worked on the immune system there, and did some of the first analyses at CERN on the first set of data on the lecture week dynamics, W and Z, whole cross sections, things like that. So he's very much been at the forefront. And he came to UMD in 2013. He's been working on CMS since then, worked on doing more electromagnetic physics and other stuff he's going to talk about, and was the HCal, the Hadron Calorimeter, CMS Hadron Calorimeter project manager for a couple of years, which probably seemed like 10 years. And it's just hard to convey how complicated it is to be head of a project at CERN. But it's sort of like, the old saying about how, it's like herding cats. And it is like herding cats, except for with herding cats, you have a prayer to succeed. The HCal project manager with all of these different groups from different countries, you have so much responsibility and very little authority. It's sort of untenable, but that was the position we were in. I don't have too many embarrassing anecdotes, so I do have one. When we hired Alberto in 2013, and it was a very competitive year, and we brought in something like 7 candidates, and I was chair of the department, so I interviewed all of them, and I was so disappointed because none of them were the kind of physicists who I thought if there wasn't an LHC, they, could do something else. I mean, they all look like if they weren't an LHC, if there was no LHC, they'd be driving for Uber or something. Alberto walks in, and I gave him an exam, and he understood the difference between S channel and T channel, and it was fantastic. So afterwards, Melissa Franklin called me up and paid me a real compliment, and our physics department compliment, and she said, "You got the best one." So that's the only semi-embarrassing.
Yeah.
Okay, so Alberto, take it away.
Thank you very much for the introduction. Now, I cannot really say that it's a pleasure to be here because I teach in this class 3 times a week. But at least this is a different occasion. And what I will be talking, we'll have to keep you awake as I do for 50 minutes. We'll be doing so by talking about what we're doing at the CMS detector at CERN, at the LHC, to investigate the problems and questions open in the standard model of particle physics. My title, I kept it short to keep the fonts large, focuses on the present and the future of particle physics. But let me start with a prologue about the past, and actually can't go further past than this, to give an idea of what we are doing in high energy physics. So when the big picture of HEP, so the plot here shows the history of the universe. We started with a fixed amount of energy at mass, we think at least. We had Big Bang, expansion. We saw a great talk. It's awful to have a talk after a great one last week about the universe expansion. we have the matter changes temperature, energy density, and undergoes phase transitions. So in a nutshell, what we're trying to do at the HEP, in HEP, is trying to get a probe for the early stages of the universe expansion. Now, what is the Big Bang now? We can look at the cosmic microwave background. This is the oldest light produced in the universe. When 300,000 years after the Big Bang, first neutral atoms formed, the fog cleared, light went free. And today, if we look at it, of course, after we subtract the background, we can get an idea of can give us an idea about the original structure of galaxies and galaxy structures in the universe. So let me move to what I'm doing. What we do, we look at time after order of 100 picoseconds after the Big Bang. This is one of our first 13.6 TV events. It doesn't look very Big Bangy. Maybe we expect to see something like this. This is a heavy ion collision, lead overhead, with an energy of about 5 TeV per nucleon. This does look like a Big Bang. Now, let me close the prologue and go into the present. I will be starting with a quick introduction about the Standard Model. What does it talk about? Which open questions do we have? And let me anticipate, I have more questions than answers in this talk, so don't expect too much. Then I will move more specifically to the work I'm doing at CERN, at the Large Hadron Collider with the CMS detector, where we try to mimic Big Bang matter and energy densities. I will then show you a couple examples of analysis with which we try to look beyond the Standard Model. And I promise I'll have two complementary approaches for you: direct searches for new physics and precise measurements of Standard Model predictions. And if there is time, I will give you a peek into the future of particle physics. So let me start with the components of matter. Compared to the Big Bang, this is still present. In the 30s and 40s, and then later 50s and 60s, cosmic ray experiments, first accelerators, a slew of new particles were discovered, to the point that Lamb suggests the punishment for those who found new particles rather than a Nobel Prize. So it's a big mess. In 56, the Eightfold Wave puts everything in order. We know that all these set of new particles are just composite of a smaller number of fundamental components. So we now know that we have a dozen matter particles, quarks and leptons. They interact by exchanging force carrier bosons, and the Standard Model of particle physics describes these interactions. So here's the Standard Model. I already say that I hate the Higgs is the 17th particle. It just breaks the symmetry of all plots. Standard Model is pretty simple to start with. It has a few key assumptions. It's a relativistic gauge invariant quantum field theory. It has symmetries, and to each symmetry we have a corresponding conserved quantity. We were lucky. The photon has no electric charge. Gravity is negligible. We can just disregard it. But most importantly, perturbation, expansion works. That is what allows us to make predictions, which have been tested over decades of experimental measurements. Unfortunately, I cannot not talk about the Higgs mechanism. Everything is great, but there is a problem. The weak forces are short range. The bosons carriers of the weak force have a mass, and mass terms break gauge invariant. They are not gauge invariant. The Higgs, you know, my despising it, it's a mathematical solution. We add two complex scalar fields, 4 degrees of freedom, we break electroweak symmetry, and we consume 3 of these degrees of freedom to give mass to the weak bosons. And the remaining one is the Higgs. So we know that the Higgs boson must exist. A very important prediction of the Higgs model is that this boson couples with matter particles with a strength that is proportional to their mass. And gosh, this is a plot we submitted to, that was submitted to Nature, a summary of a decade of Higgs measurements, which you see that this prediction is verified over 3 orders of magnitude. So that particle we saw at 125 GeV has the properties of the Higgs. Today, we have hundreds of Higgses, and we can see it in a very disparate final states, including very rare ones, such as a Higgs 2 mu mu. I don't think you need to look at the data minus background plot. If you stare long enough, you can see 3 points above the red line in the plot on the top. That's a 3 sigma evidence. Is everything done? Well, as I promised, we have many open questions. So the Higgs crowns the success of the standard model, but we know that the standard model is an effective field theory. It works up to some probably very high energy. Among the questions, do we have more matter? Are we done with matter? Or do we have more? Is a single Higgs field enough to explain the whole business of electroweak symmetry breaking? Is the Higgs also the source of neutrino masses? And if so, why quarks minimally mix while neutrinos maximally mix? But these are only the problems within the standard model. We have even more. Do we have anything that is not at all in the standard model? Astronomical observations, such as the velocity of stars inside galaxies, and cosmological arguments tell us that the standard model, by great, is describing 5% of the matter and energy in the universe. So what is this dark matter? We know it interacts gravitationally. Does it have other interactions? What is its origin? I will want to focus my first part of the talk on dark matter business. So here's a way of measuring, observing dark matter. It's a fake Feynman-like diagram. From left to right, your standard model producing dark matter. That's what we hope to do at colliders. From right to left, you have a dark matter annihilating and producing standard model particles. From top to bottom, you have a scattering of dark matter on standard model particles. It's great, but there's a big caveat here. It assumes that dark matter does talk somehow to the standard model particles. So I need to keep my colleagues happy, so let me show some plots from others. The direct detection of dark matter is the goal of the LZ experiment. It's the top to bottom in the Feynman diagram I showed before. We want to measure dark matter hitting, scattering over xenon atoms and ionizing them. The plot on the right is the current latest measurement by the LZ collaboration. It sets limits of this WIMP, weakly interactive massive particle. It's a dark matter candidate. The cross-section dark matter standard model nuclei versus the mass of the dark matter candidate. The limits are already close to the prediction, to the expectation for the experiment, and there are studies ongoing with twice the data to improve them even further. If now I look left, which side is this? Right to left, we can look at the effects of dark matter annihilation. This is the goal of the Hawk experiment. What they do is measure the flux of cosmic rays on the Earth. If you see any discrepancy between the predictions and the observation, you can relate them to dark matter annihilating and producing more standard model particles. The plot is again the latest result for the all cosmic rays fluxes. I want to point your attention to this logarithmic scale. They go up to energies of peta electron volts, while what I'm doing at LHC is off the scale, slightly off the scale on the left side. So finally, let me say, what am I doing? So first of all, 2 words on the Large Hadron Collider. It's a 27 kilometers ring. It has 4 collision areas located 100 meters underground. It consumes as much power as a mid-sized town. For those who ask me if I do anything that has to do with energy conservation. It's more energy consumption here. Protons are collided in bunches, about 10 centimeters in longitudinal side, tens of microns on the transverse side, with 300 bunches per beam at the same time, about 100 billion protons each. Avogadro's number is huge. That photo there contains, that can contains all the protons needed for the LHC lifetime. We use about a couple nanograms of protons per day. In one of those collision areas, the compact muon solenoid detector is installed. It's compact but not small. It's about a cylinder, 15 by 15 by 30 cubic meters. It weighs as 2 Eiffel Towers put together, just to give a size. We produce, as the bunches are colliding every 25 nanoseconds, we can only save about a fraction of these collisions, about 10,000 per second. But that's a lot of data. Last year, 100 petabytes were written to tape. The collisions happen every 25 nanoseconds. And as we know, light travels 1 foot per nanosecond. The detector is bigger than 25 feet. So as particles produced at different collision times are crossing the detector at the same time. It's a big mess to assign them to the right event. We measure their properties by using our 80 million independent readout channels, 80% of which are just in a very small box close to the interaction point. It's a great photo, but here's a schematic view of the detector, in which you see the various subparts of the detector, and there is a picture of a person to give an idea of the scale. Now let me say a few words about how a detector works. This is a transverse view of a slice of the detector. The beamline is going perpendicularly to the screen on the left side. The whole detector is embedded in a magnetic field generated by a solenoidal, by a superconducting solenoid. So charged particles will bend in the magnetic field, leave a track in the inner tracker. From the curvature we can tell their momentum. Then electromagnetic objects, electrons and positrons, are stopped in the electromagnetic calorimeter, which measures their energy. Hadrons, neutral and charged ones, are stopped in the hadron calorimeter. Muons can go through the whole detector. They bend in the opposite direction in the muon chambers, and we can tag them quite easily. The events are cylindrically symmetric. The beam arrives perpendicular to it. So if we see any imbalance in the transverse energy or transverse momentum on this plane, it must correspond to invisible particles that escaped without leaving any signal. That's the case of neutrinos, or if you are extremely optimistic, dark matter. Now, we have this. How do we get it to work? As I anticipated earlier, we need managers. So here's a picture of our the CMS management board. My name is small, somewhere in yellow. The yellow, blue, and the brown boxes are the executive board. We have the coordinators of the event selection, of the computing, of the physics. The unlucky guys are the ones in the yellow, the detector system managers. And each one of them, here's an aptly chosen example, have their set of level 2 and level 3 managers. What could get wrong with lots of managers? Well, we actually need somebody to do some work. So here's the photo, the people who are actually doing useful work. The CMS collaboration, as of yesterday, is composed of 6,100 members. About half of them are physicists, postdocs, and faculty. We have about 2,000 graduate students and 1,000 engineers and technicians from 250 institutes from 60 countries. In my plots, you will see a funny way of measuring data. It's called the luminosity. So luminosity is a quantity that is proportional to the number of protons that collide and inversely proportional to the size of the beams. The higher, the better. It's measured in funny units, 1/area, a barn. The barn is the size of a uranium atom, so it can tell you when people came up with these studies. The product of luminosity and a process cross-section gives you the expected number of events in your data sample for that process. The plot shows the luminosity we integrated year after year since the beginning of the LHC project. And the increasing slope tells us how the LHC accelerator improved its performance and detectors were able to collect data more efficiently. A similar plot is our publication pipeline. I can proudly claim that I authored more than 1,000 papers, about 100 per year. Anybody who has access to the slides, I put a link to the interactive plot, because every point, every marker is a link to the relative paper. I tried to click for mine, I couldn't find them though. A similar plot, but in the other direction. What do we do? What does this tell us? So 2 highlights. Just to start bringing home the message that the standard model is amazing. This is our summary plot of the measurements of standard model cross-sections. There is a match between measurements and predictions over more than 8 orders of magnitude. And this plot has been around so long that it got its name, the stairway to discovery. Although, when I think about the stairway, I don't think of me going down a cellar. My personal contribution to this is the measurement of the triple vector boson final states, one of the last letters there. What about new physics? So here's a summary of our results, and I have 2 more in the backup. If you can't read it, no worries. In fact, legibility of this plot is our metric for success. Every year it becomes less and less readable. Now, I think I promised some time ago to talk about dark matter. So let's see what we're doing. The WIMP paradigm, so the idea that there is a single new particle that needs to be added, that's dark matter, is sort of losing a bit strength. So now there are emerging models in which people suggest that there exists a dark sector similar to the visible one, and most importantly, as complicated as it is. There is an interesting thrust into long-lived particles. The naive explanation is if they were short-lived, meaning they have interaction, they interact easily with standard model, well, we would have discovered them already. The plot here is a sketch of various types of long-lived signatures. I want to focus on the emerging jet one. So what is this telling us? The idea is natural. Quarks are interact among themselves via gluons, and QCD, quantum chromodynamics, tells us about how they interact. So let us posit that we have ordinary QCD and we have a dark QCD with its own gluons and quarks. And the two, ordinary and dark QCD, can talk to each other via a heavy mass mediator that gives us this weak link between the two. So what happens? Dark quarks hadronize like normal quarks. They produce a jet of dark pions, dark rhos, dark kaons. The dark proton is stable as the standard model proton, and in this model it's our candidate dark matter. It's our dark matter candidate. Now, since the connection between ordinary and the dark QCD is weak, these dark pions can decay to standard model particles, but they do so with a lifetime, with a long lifetime, displaced from the production point. So what we aim to do is tag this emergingness. Now, am I starting complaining here? No, next slide. We need a way to tell whether these jets are ordinary or displaced. So let me make a quick reminder. We have a charged tracks moving in a solenoidal field. They go through a helix. We need 5 parameters to describe it. The curvature, which is the inverse of the momentum, their displacement with respect to the proton-proton interaction point on the transverse plane and along the beamline, and 2 angles to tell the direction. The plot on the right is calculated on a jet-by-jet basis. You take a jet, you calculate the average transverse displacement of the tracks associated with that jet. Ordinary jets are closer to the interaction point. As you increase the lifetime of the dark pion, you get that the average transverse displacement is further and further away from it. This is when I start complaining. Analyses are very, very complicated. So we have a fixed number of pieces of information, and we have to try ways of combining them to find, to use them in a more clever way, and overcome new challenges. For this analysis, one of the main background sources is an incredibly rare way of failure in reconstructing the interaction point of the proton-proton collision. For this analysis, we define this quantity alpha 3D. In a nutshell, is the transverse momentum weighted fraction of the tracks in a jet that are compatible with coming from the primary vertex. It's a number that is close to 1 for ordinary jets and closer to 0 for emerging jets, in which fewer tracks belongs to the primary vertex. Okay, now the big question, did we find the dark matter? No. We set limits on the dark pion lifetime as a function of the dark mediator between the two QCDs. Now I want to note that this is my second search. The first one presented 6 years ago. What happened in the bito? The theorist colleague who presented this model told us, wait a moment. I told you that these dark pions can only decay to light quarks, up and down. What if they decayed to bottom quarks? Okay, fine. Flavor-aligned model. No new physics here either. And I think our friend got out of ideas. So we're cutting phase space for new phenomena. Now, let me close the dark matter part. I mentioned that it's a big question, but the standard model does have other open questions. In this schema, were some of the big questions and some of the models that have been presented to solve them. The I mentioned the electroweak symmetry breaking issue. What's the origin of matter and antimatter symmetry, asymmetry? Quarks and leptons, are those really fundamental or composite? And finally, are the standard model fundamental parameters finely tuned, meaning they come up as subtractions of huge numbers and end up being exactly what we observe? So that's the problem that comes as a naturalness issue. Let's look at that. So we tried to look for a new vector boson that would be a partner to our W vector boson. And this is the most direct type of search you can do. You make a plot, look for a bump. It has a moderately unusual signature with very high transverse momentum photons, and that was our contribution for all CMS analysis. Now, the strategy is straightforward. You make plots, like the one on the right. You look at the data and compare it to templates corresponding to your new state with different masses and try to see what is the best fit. We look, I have to note that we look for W's decaying to leptons. So again, do we have a new particle in sight? No, and that's it for me. Third time I look for new physics and I found anything, I'm done with that. I'm going to be doing only precision measurements so far. Our measurement is the black line in this plot, and you see that it's always boringly consistent with the predictions. But what about the red one? That's what left me moderately disappointed. That is the result of the W gamma analysis with the W decaying to jets. We had a 3 sigma XS at 1.6 TeV. So if you want, this would be the punchline for my talk. I managed to destroy one of the most interesting XSs that the CMS collaboration ever had. Well, why did I specifically look here for job security? Because it's a model presented by a colleague to whom I have to say, sorry for the Nobel Prize, gonna be the next time. Now, I promised to show complementary ways of testing the standard model, and those constituted by precision measurements. So the standard model has been, we've been performing measurements for decades, and some of them achieved a staggering precision. For example, the fine structure constant is known to parts per billion. In the standard model, as introduces relations among its parameters, and for example, we knew about the top mass of the Higgs before we saw them. So we can exploit these to close the theory and over-constrain it. I mentioned the fine structure constant, but I have two plots about the measurement that we do at colliders. That's the strong force coupling alpha sub s, shown as a function of the exchanged energy, and alpha sub s measured at the value of the Z mass. Now, these are multiple measurements, different experiments, different colliders. We have electron-proton, proton-proton, proton-antiproton measurements. They all match the standard model predictions. So what I looked at is the W mass measurement. Now, there is no prediction in the standard model for it, but there are relations with other parameters, such as the top quark and the Higgs boson, as shown in the plot. But if there were new particles with weak charge, they would affect this plot, these relations, and we could at least infer the existence of new physics. This is a very challenging analysis because the world average has a precision of 0.02%, and yet it's one of the leading uncertainties in the global closure test. So how do we measure the W mass? The rough recipe: you take W's, make them decay to leptons. You build a a quantity like the W transverse mass using the neutrino, using the transverse missing energy as a proxy for the neutrino transverse momentum, and then you compare your plot with templates corresponding to different values of the W mass. The plot on the right is just to tell you that's out of the box. So out of the box, without doing any calibration correct, we get that kind of agreement. That's a W transverse momentum distribution. W transverse mass distribution. The big uncertainties are the energy scale of the leptons, the incomplete knowledge of the proton, and the modeling of the W transverse momentum. And here comes my pedagogical slide. So I mentioned as inputs the lepton transverse momentum on the left and W transverse mass. Now let's imagine W's being produced at rest. The two plots would have a sharp peak at half the W mass and at the W mass. Now, W's are produced with momentum. What is the effect of the finite momentum of the W? That's the blue curves. On the left, the lepton transverse momentum distribution gets deformed dramatically. On the other hand, when I introduce the detector in smearing, so the uncertainties on the measurement, it doesn't change much. So the lepton transverse momentum is mildly affected by detector resolution, but it has a large dependence on the W transverse momentum, which is afflicted by large theoretical uncertainties. On the other hand, the W transverse mass is a sort of invariant quantity. It's largely independent of the W transverse momentum, but it uses missing transverse energy, which is very complicated to measure precisely. So the detector resolution is what destroys the beauty of that plot. So I realized that I had my group work on alternative processes, tasks that address both, only either one on the postdoc, one the student, one won, the other didn't. I'll get there later. So the CMS measurement used the lepton transverse momentum to perform the measurement, but arguably using adding the transverse mass is a way of improving it. So we set to work on an algorithm to improve the measurement of the transverse missing energy. I'm showing we developed a deep neural network algorithm which succeeded in improving the resolution of our measurement as a function of the number of concurrent proton-proton collisions in an event. Now, I'm showing you in this slide a schema of the neural network, just to convince you that I'm smart. And the money plot is the one on the right. The blue line is our algorithm, while PF and PAPI are particle flow and pile-up per particle identification. It must have been an Italian who came up with that acronym. They are the two algorithms used in CMS. And nobody thought we could improve the transverse missing energy resolution. Now, look at that plot, and if you're wondering, yeah, great, but is that really a big deal? Now, that plot goes up to 40. Let me show you an event that we took less than a month ago. 206 concurrent proton-proton interactions. Don't ask me how I can tell what's going on here, but we know that at least 205 are not particularly interesting. This event is special now. In high luminosity LHC, this is going to be the norm, the average number of concurrent interactions. So let's go back to the measurement. So ultimately, we relied on the lepton transverse momentum. And the plot here is absolutely shocking. We have more than 100 million W's, and the agreement between data and Monte Carlo is within 0.1%. And this is due to one of our key contributions to the measurement. I mentioned the deep net algorithm. The other is a study of the next to leading order, next to leading log corrections to the simulation. The more ends, the better. And this is the first time that this precision has been achieved for a measurement like this. And it allowed us to calibrate the muons directly using the simulation without touching the Z. I can't go into the rabbit hole of telling you what are the two tests that we could do with the Z, but please ask me when I'm done in the backup. I think I mentioned that these measurements are difficult, so let me insist on that. These are a couple of the problems that Atlas and us had. On the left, I have a plot of the data over Monte Carlo prediction of the electron energy over momentum ratio as you go around your detector. The modulation that you see with uncertainty larger than the uncertainty is due to the deformation due to gravity of the calorimeter. So earlier I lied to you when I said that I can disregard the gravity. The plot on the right is a very peculiar issue that we found. Now we have a simulation, and the simulation propagates particles through your detector. And at each border between one surface to the other, it truncates the position with a precision of 0.1 microns. Well, we found that after about a couple meters of propagations, positive and negative muons resulted in bias in opposite directions with respect to the expected position. Recompiled the software, changed the precision to 1 nanometer, and they went one up to the other. I had to make by hand this plot because my collaboration forbade me from showing the one that they made. It didn't get approved. I told them I would have drawn it on the whiteboard in case. If you're wondering, oh, gee, you have a big problem on the left. We're talking about particles being a couple microns away from where they're expected after meters through the detector. Finally, the measurement. The measurement solved, probably, the conundrum opened by the CDF measurement, which is about 7 sigma off. CMS is consistent with the electroweak fit. The future circular collider will say the last word. Again, the standard model comes out the victor. Yeah, but also us to some extent. In 2025, the Atlas, ALICE, CMS, LHCb collaborations received the breakthrough prize for these and other analyses that were performed with the data collected between 2015 and 2024. A prize shared in total with about 10,000 people, but I managed to get at least 4 of them in the department. Now, how does it feel sharing a prize with 10,000 people? Well, I'm still proud. In fact, I remember my 2012 Nobel Peace Prize, which I shared with 500 million people. So, 2 billions of a prize is small, but strictly speaking, is strictly larger than 0. So let's move to the future. Let me close with the present. Let's move to the future. For what is next at CERN? This is the plan of the LHC and high luminosity LHC. We're currently collecting our last 6 months of data, and then we will turn off everything to upgrade the experiments in preparation for the high luminosity LHC run. The high luminosity run will take about a decade, where the LHC is upgrading. We'll try to increase the energy, and the luminosity will increase by a factor of 3 to 4. CMS will be upgraded. I point out here the improvement in event selection. we will increase by an order of magnitude our trigger latency and trigger rate, which means we will have more time to make more complex selections and save more data. The physics goals include the measurement of the Higgs couplings with a precision of the order of 1%. We will have 10 times the data that we have now to look for beyond the standard model signatures and rare standard model signals such as B2 mu. For the preparation, we're building new detectors. In particular, we have to cope with the radiation and a very large number of concurrent collisions. There's a new paradigm emerging in calorimetry, the high granularity. CMS will replace the end-cap calorimeter with a high granularity calorimeter, which will allow us to take literally photos of the shower. Those are real data from a test beam of a prototype. I would like to say in 5 dimensions because we have also time and energy in these measurements. So the number of readout channels will increase by 4 orders of magnitude, and this detector will constitute a milestone for the next generation of machines. So what are we doing here, or rather in the PSC? The HGCAL will have 2 parts. The part in the high radiation area will be silicon pads. In the lower radiation areas, we will have plastic scintillators glued to electronic tile boards, such as the one pictured in this slide. 4,000 tile boards will be produced, half of them in Europe, the other half in the US, and the UMD CMS group is responsible for testing the 2,000 boards that will be produced in the US and make sure that they can be used in our detector. And this is tough. These guys will go underground in a high radiation area for 12 years at minus 30 degrees. They will not be allowed to fail. But for now, we're having fun. We started the tests and will continue for the next year. And over summer, we had a team of undergraduate students, some good, some not so much, performing projects to automatize the procedure. For example, here I'm showing our test stand for taking high-resolution photos. Students developed a neural network algorithm to compare them to templates to identify, for example, assembly mistakes. In the backup, I have photos from our infrared sensor test to look for hot areas that typically correspond to assembly issues, and a CERN-hosted website to report or automatically report the content of our testing database. That's for me, so that project managers don't ask me to give them reports. They can just look online and see what's going on. So here's a photo of some of the folks that have been, they are working in our lab at the moment. We have lots of undergraduates, grad students, and postdocs. I'm not there, that's why they are all smiling. I think I have time to tell you about a look after high luminosity LHC. So the current long-term perspective goes up to the 22nd millennium. I'm not making that up. I got the number from the deputy project manager of the FCC project. So we'll start with a circular collider electron-proton, positron, or a linear collider that can go at higher energy, followed by a future circular collider, an hadron machine, at about 90 TeV at the moment. That's the idea. I have the goals of all the electron-positron machines in the backup. I'm putting here the ones for the hadron machine because they are crazy. Tens of billions of Higgs bosons and thousands of billions of top quark pairs. That's what we will have. I don't think I'll be looking at them in 2100. I point here just because I'm one of the co-authors of one of the reports, a link to the SNOMAS panel report, which defined the priorities of US particle physics. The SNOMAS report, the European strategy report, they all agree that the next step is a Higgs factory to study the Higgs in detail. So here comes my last timeline. So how far should we go? So right now we are in the high luminosity LHC. We are upgrading, the upgrade projects are well underway, and they are on schedule for getting data until 2040. In 2035, beginning of construction, 2045, the operations until 2060, future circular collider electron-positron. There are no technical showstoppers. They are finishing the investigation of where to cut the tunnel, and there is ongoing R&D for the detector designs. I didn't talk about it, but some of our grad students are doing a simulation for FCC detectors. The last, the beyond the day after tomorrow future, construction starting in 2060, operations from 2070s to 2100, FCC HH. Here we do have a big R&D topic. We need high field magnets to keep, to fit 90 TeV protons in a 90 kilometers ring. So with this, let me close. So wrapping up, I think I convinced you that the standard model is going strong. We have decades of experimental results that confirm its validity. We're trying to poke holes in every direction, but so far, all the clever extensions of it have been tested with precision measurements and direct searches. It gave a small flavor of what it happens, how it feels working in a collaboration with thousands of people. And most importantly, we have a very long-term plans defined. The long-term plan is defined until 2040s, which is when I can probably retire. If you are very optimistic, you can go to 2100. I realize that people born when I retire can almost retire there. So let me conclude by saying that there is a lot of job security here, I guess. Thank you. Yep. If there is any question, Drew talked about my accent. I have a backup slide about that. Yes, please.
Sorry. My question was psychological.
Yes.
Because I'm, of course, completely convinced on the greatness of the physics enterprise and so on. But do you find, working with graduate students and maybe undergrads, do you find they're up for this long-range, long-time-scale mission, ultimately exciting, that they have to live? They have to retire?
Yeah, but I shouldn't say anything negative about it, but one thing we can say is that as the projects are becoming bigger and complicated, the time it takes to build, design and build detectors is longer. So I cannot, I think we might have generations of students who write a thesis about detector development without physics, without an analysis of data, because we cannot have the data. The FCC EE will start construction in 2035. HLLHC finishes in 2040. FCC EE 2045. Who starts in those 5 years will be working on preparation for FCC EE analysis, for example. But the whole environment is extremely exciting. We have lots of students that are working on the development right now of detectors for the FCC-EE. And we started a couple of years ago. We've been, for example, specifically in our group, we have an expertise in calorimetry. So we're studying dual readout calorimeters. Calorimeters in which you can separate the way the light is produced and use this different information to measure the energy of jets more precisely. This dual readout calorimeter has been around for years, but we haven't had any actual working implementation. And now we're looking into all of these directions. So there are lots of interesting projects that are ongoing. If you're interested for 2070s is behind the corner. Huh? Yes, sir.
So just a dumb question. These are very ambitious plans. I assume they're not going to be done cheap. And so one question is, how much money does it cost to build one of these?
To build it.
And the second one is, let's say when the LHC was built, there was a clear physics target. You were going to discover the Higgs,
Yep.
or rule it out. Either way would be exciting. And if you were lucky, you would discover extra dimensions or dark matter or whatever. It looks to me like these other ones, there isn't sort of a guaranteed, Nobel Prize at the end of the road, etc. So, given the large scale of money and the, gee, we're going to get on a ship, go across the ocean, and hope there's land on the other side. Can it, politically, can you push this? Well, not you, your community, push this through to 20, for the rest of the century?
So the community of particle physicists, both US and Europe, they're all committed to, all decided that the next step must be, we found the Higgs, we must measure its properties. In the past, when we had not yet discovered the Z and the W, still we could use them to get an idea about looking at precision physics of the Higgs gives us an idea about much larger scales in which we can see if there is anything there. And that's the idea of these precision measurements. About the money. No, that was on my accent. Am I? Okay, great. So here's some of the numbers. For example, FCC-EE, we have the TeraZ project, 6 10 to the 12 Z candidates fully reconstructed. The cost is 12 billion Swiss francs. 2/3 of them are only for civil engineering, which is shared with FCCHH. FCCHH is 17 billion if we bought it now, I'm afraid. And 10 of them are only for the magnets. 7 for services, and we get the tunnel for free, because it's the one built for the FCCHH, for the FCC-EE. So this is an idea of the latest costs. In the big picture of things, is nothing. Yeah.
I mean, that's super cheap per Z.
Yeah, exactly. Yes.
It's a very nice talk. So you said
Yes.
You said you're planning to increase precision or number of channels that you're reading out by shorter than 90. So I'm just trying to think about data management, because you said you're starting, right now you have 100 petabytes per year. Are you planning to store 1,000 exabytes, or so it's a yottabyte a year, or is there some sort of data compression or improvements to triggering?
So I think we want to take as much as possible. Okay. I have a slide of that. So I have to pass through the slides. Gee, this came up when I was having a group meeting. I felt very... What is these AI things? I hate them. Anyway, and I was not even gesticulating much. Anyway, okay, here's the big data.
This is my stuff.
What we have? Storage, streaming. The small points are the data that we plan to collect. So in high luminosity LHC, we expect about 800 petabytes per year. Last year, it was 100. It's about an order of magnitude. That's the idea. The big point is 40,000 exabytes is what we produce every year if we were saving every event that we produce. That's to give an idea of what is happening. So if you want, right now, you can do the math. We can imagine that FCC-HH might be producing about an order of magnitude or two more data than high luminosity LHC. So per year, it would be order of 10 exabytes. For 30 years, we're still below what AWS has by an order of magnitude. Yeah. At least we have useful data. Yeah. Yes, do.
So AI is a big deal now. And I like the plot of looking at listening to you. But you must be doing other things with AI than just that. What else is going on with AI?
Let me say something crazy.
Is there anything to replace you with an AI yet?
Well, I hope it happens after 2040. One interesting thing we are doing. I mentioned that for high luminosity LHC, we are increasing the latency of the trigger system and the rate of particles. People are studying now, for that period and beyond, a way of writing machine AI-based software and load it onto FPGAs so that we can have AI running at the trigger level to select our events. That could be one of the ways in which we use the additional time to implement more complex event selections. But then I don't know what, it's a bit of a black box. I don't know if I would like that to be in parallel to what we do. Yes.
Just a minor question. With all these magnets and detectors, do you use a lot of rare earths?
Good. Interesting question.
I'm just curious.
Yes, but at the moment, the focus is more basic. It's not so much the procurement of the material. The focus is basic. We cannot get a magnet with a field above 14 Tesla. And that is what we need to fit in the 90 kilometers ring our 90 TeV protons.
So you would need more.
Yeah. The R&D is going into doing that, producing magnets that can get to that field. These are all superconducting magnets. There was an idea for room temperature magnets that could be fit into the LHC ring to make an upgrade, to have another machine called HE LHC, high energy, at 20 TeV, but 20 to 30. But that would be a small increase compared to the original FCC-HH plan to go to 90 TeV. That opens a really big space for new physics. Thank you.